Hello students, welcome to Educate. In the previous classes, we have started the bonding in coordination compound. In that topic, we have discussed about the valence bond theory. The valence bond theory usually explain about the shape of the coordination compound and the magnetic behavior of the coordination compound. That is, the compound is diamagnetic or paramagnetic. Based on that, here is a question about that we will discuss. So listen here, question is, this is a coordination compound is here given and its dipole moment has been given. And you have to predict the geometry of the complex. So listen here, coordination compound, here number of the compound is 4. So since the coordination number of the compound is 4, so the compound may be tetrahedral or the square planar. So what is here the compound is tetrahedral or square planar, about that we will have to predict. So listen here, dipole moment is given, so we can find out the number of electron in manganese. The dipole moment of the compound has been given, so we can find out how much number of unpaired electron manganese have. We will calculate here also. Another one here, watch out, when there was tetrahedral geometry. So tetrahedral geometry was when the hybridization was sp3, and during that course the pairing of electron were taking place. So number of unpaired electron there be 0. So dipole moment also equal to 0. But here in the examination that you can calculate fastly also. So here the molecule have, the coordination compound has dipole moment. So there is no pairing of electron. So that means the coordination compound is containing the unpaired electron. Okay, so unpaired electron. So when there was no pairing of electron, then hybridization were, in that case the hybridization were D2sp. Okay, so D2sp. So in the same case, let's see here, just check. Dipole moment is 5.9. So dipole moment, you know, that is equal to root under n into n plus 2. That is 5.9. So that will be equal to 5.9 Bohr magneton. Unit here is 5. So dipole moment has been given 5.9 Bohr magneton. So that will be equal to root under n into n plus 2. Now here to bring the n, the value of n, that is here under root will come this side. So that will become a square. So that will be 5.9 into 5.9, that you will have to do. So square, that will be 34.81. So here 34.81, that here Bohr magneton, that's a square, that is equal to root under n into n plus 2. So now calculate here 34.81, that much will be equal to, when you write there, so Bohr magneton, that's a square. Okay, ignore the unit here. Better is ignore the unit. So otherwise you get confused. But you will get the marks here. If directly you will write that is square planar. So that one will be equal to n square plus here 2n. That means n square plus 2n minus 34.81, that equal to 0. Formula you know, n will be equal to minus b, so that means minus 2 plus minus root under b square minus 4ac upon 2a. That formula you know already. So that means n equal to here, when you will calculate n equal to here, that will be 5 usually, 2 to the 4. So, or 2 to the 4. Firstly, minus 2 plus minus root under 4 minus 4ac, did that into 4, 34.81 plus 34.81 into 4 upon 2a. This one here upon 2. So n will be equal to minus 2 plus minus root under, calculate here, 34.81 into 4. How much? 34.81 into 34.81 into 4. So that will be equal to what? 139.24 and plus 4. So that will be 143.24. So that will be equal to 143.24. This one here. Now find out the under root of 143. Upon 2. So 143 under 0.24, find out their square root. That is 11 point, this one 11.9. So nearly about it will be 12. 12 12 144. So that will be nearly about 12. 12 minus 2, 10, 10 upon 2. That will be 5. So here number of unpaired electrons is 5. So how the bonding is taking place here? Till here, I think clear here. This one, how I have calculated? So number of unpaired electron. That means in that case, the manganese, in the manganese, number of unpaired electron is 5. So how the bonding is taking place? Let's see. Manganese atomic number 25. So that will be electronic configuration will be this one. Now manganese in which oxidation state? MnBr4 minus. So what is the oxidation number of manganese? That you will have to calculate. So you don't know the oxidation number of manganese. So X plus 4 into minus 1, that equal to minus 2. So X plus X minus 4, and that will go there. So X will be equal to here minus 4 here. So X equal to minus 2 and X plus 4 into minus 1, that equal to minus 2. So X minus 4, so plus 4 here. So X equal to plus 2. So oxidation number here manganese, that is plus 2. So here the 2 electron will be released from 4s. So manganese, electronic configuration of manganese in plus 2 oxidation state, that will be equal to 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5. So what happened? Since Br minus is a weak field ligand, Br minus is a weak field ligand, so it will not induce pairing of electron. It will not induce pairing of electron. So what will happen? So here it's a 3D in which there will be 5 orbital. There will be 3D here. It's 4s, and then after is here 4p. Is 4s, and here 4p. This one. So already pairing electron here is. So to that, here it will not do pairing of electron. Okay, no, shape is here tetrahedral, not square planar. So sp3 here, so 4p, so shape will be here sp3. Hybridization of this will be sp3. So sp3, so the 4 hybrid orbital, 4 sp3 hybridized orbital will arrange in 3-dimensional space, so that the electron present in sp3 hybridized orbital that will experience the least repulsive force. So here is 4 hybrid orbital, and in that one the each Br minus will donate their electron and form the complex. It is sp3 hybridized orbital and sp3 hybridized orbital. So shape will be here tetrahedral. So shape will be tetrahedral. And magnetic behavior, it is paramagnetic. So what is here? Coordination number of the compound MnBr4 2 minus, that is 4. So shape may be square planar or the tetrahedral. So to be a tetrahedral here, so like this one bond has taken place. So if shape will be not a square planar, because to be the square planar the d orbital have to merge together, and for that d orbital is not here, so pairing of electron taken place. Pairing of electron will take place there, but Br minus is not a strong field ligand, it's a weak field ligand. That's why when the ligand Br minus will approach towards Mn2 plus, it will not induce pairing of electron. So when it will not induce pairing of electron, then the s1 orbital of s and the 3 orbital of p, they will merge together and form 4 sp3 hybridized orbital. So this one 4 sp3 hybridized orbital. In this 4 sp3 hybridized orbital, that means this sp3 hybridized orbital will arrange in 3-dimensional space in tetrahedral manner, and in those sp3 hybridized orbital, each Br minus, the ligand Br minus will donate their electron and be bonded there covalently. So shape here tetrahedral, magnetic behavior paramagnetic. Okay, if I have told a square planar, shape would be, so that will be wrong, not a square planar, tetrahedral. Okay, might be there be slip of mind. Now let's see, here is limitation of crystal field theory. Let's see limitation of crystal field theory. So which one is most important here? Limitation. One is here, lots of assumption there is, okay, because hybridization itself is a hypothetical term. Might be you know, hybridization itself is a hypothetical term. Actually, that's not takes place that has been assumed that would be taken place. So now the valence bond theory here, first one is lots of assumption. Magnetic data it had told, but I have told you also that if there be only presence of electron, you cannot say that the molecule will be paramagnetic or ferromagnetic, depending on there be pairing of electron or not. If there be the pairing of electron, that means electron means there tiny magnet, that is domain, about that you will study in the higher classes. about the domain. So if the domain will, in some cases, not only in some cases, at a number of places, the two domains become in opposite direction. So when you will watch out the number of unpaired electron, then you will say that the compound is ferromagnetic. But because one domain, when in a number of molecules, there be the domains align in opposite direction. So the dipole moment of one domain cancel out the dipole moment of other domain, and during that course the dipole moment becomes 0. So by considering the number of unpaired electron, the compound would be ferromagnetic, but due to cancellation of the dipole moment of the domain, the compound will behave different magnetic behavior. So that is here. That's the second point is it does not give quantitative interpretation of magnetic data. Third one is why the coordination compound shows color. That's valence bond theory has also not explained. The coordination compound shows color. Why the coordination compound show color? About that, the valence bond theory have not given any explanation. Next point is it has also not told the thermodynamic stability or the kinetic stability of the coordination compound. Okay. Next one is here in compound there, when the coordination number was 4, then there was difficult to predict that the shape will be tetrahedral or the square planar. When the coordination number was 4, so it was difficult to predict that the shape of the molecule will be tetrahedral or the square planar, because in the coordination compound here, because the valence bond theory have not set a clear-cut demarcation between the strong field ligand and the weak field ligand. So that is here. So that means here do not explain that square planar structure or tetrahedral structure. Now it do not distinguish between weak field ligand and the strong field ligand. So that where the limitation of valence bond theory. Some of the weakness of valence bond theory has been recovered by the crystal field theory, also called crystal field splitting theory. Okay, so now let's see in crystal field theory. First one, in crystal field splitting in octahedral complex. The crystal field theory has explained about why the coordination compound show color. In addition to that, it has also predicted the shape of the molecule. So let's see here. First one is crystal field splitting in octahedral coordination entity. Okay, so listen here. Before that, before explaining about that theory, first of all, just consider about the shape of d orbital. I have taught you about the shape of d orbital in d block elements also, and in this one we will discuss about, we have already discussed about the shape of d orbital, shape of d orbitals in the chapter of d block elements. Now that has a utility here, so again I am recalling here fastly. So first one is dxy dyz. Here, firstly let's see the shape of dxy. So about the dxy shape, here x axis, this one is x dash, here y axis, and this one here y dash. So the shape of the d orbital is double dumbbell. So one dumbbell will be in this coordinate and one dumbbell will be in this coordinate. That is the shape of dxy. It is the shape of dxy. Now about the dyz and dxz, about these two, you find by yourself. It's easy. Now about the dx square minus y square. So it is x axis, here x dash, here y and y dash. So one lobe will be in this one along x-axis. In case of dx square minus y square, double dumbbell shape of the d orbital, one dumbbell will be along the x-axis and the other dumbbell will be along the y-axis. So it is dx square minus y square, and the shape of dz square will be also, that will be also double dumbbell, but shape will be in a different manner. Like here, this one, it is z axis, z dash. One lobe will be along the z axis and the other will be around this origin. It is dz square. So what happened here in dxy, dyz and dxz? The shape of the double dumbbell will be between the two coordinates, but here it's different and that of the dz square is different. So what happened? So there is 5 orbital of there is 5 d orbital, 5d orbital, and their name is dxy, dyz, dxz and dx square minus y square and the dz square. This one here, when the ligand approaches toward this, when the ligand approaches towards the d orbital, let's see here another page. When the ligand approaches towards the ligand, then the degeneracy of the d orbital do not maintain for a longer period. Okay, so the degeneracy of these orbitals do not maintain. So what happened? This dx square minus y square and dz square, that will be towards the axis of the ligand. So the energy of dx square minus y square and the dz square, the energy of dx square minus y square and the dz square, that decreases through 2 by 5, okay, that will increase by 3 by 5 delta O. Okay, that is, this one is for the tetrahedral complex. In octahedral complex, that will be different. So the energy of this one, dxy, dyz and dxz, that will decrease here. Firstly, during the bond formation, the energy of these orbitals increases, which is called, the energy of these orbitals during the bond formation increases, and that is called delta O. Okay, during the bond formation, the energy of these orbital increases by the value of delta O. O means octahedral. So the energy of these orbitals will be here increase firstly. Same dxy, dyz, where if you would like to write, then you write by yourself. This one, but the degeneracy of these orbitals do not maintain for a longer period. When the ligands approach towards these orbitals, that means d orbitals, when the ligands will approach towards the d orbitals, then the degeneracy of these 5 d orbitals do not maintain. That means energy of some of the orbitals increases and some of the orbitals decreases. The energy of some of the d orbitals increases, and of which will increase? So energy of dx square minus y square and the dz square, that will increase, because the axis of these orbitals is along that of the ligands. So the energy of dx square minus y square and as well as the dz square, that will increase. This one, so it is dx square minus y square and dz square, and the energy of the dxy, dyz and dxz, that will decrease. So it will be called T2g energy level. The energy of the orbitals which has been decreased, that will be called T2g energy level. dxy, dyz and dxz, these were called T2g energy level. And the energy of orbitals whose energy has been increased, that is dx square minus y square and the dz square, that has been increased, and they were called easy energy level. Okay guys, keep in the mind here. Just I am giving you 1 minute break. Just think over that. How is that happening? Firstly, during the bond formation, the energy of the d orbitals increases by delta O value. Then after, the energy of dxy, dyz and dxz decreases when the ligand approach towards the d orbital, and the energy of dx square minus y square as well as of dz square will increase, and that will be called Eg energy level. Okay, then after filling the electron, filling of electron, you know already Pauli's rule, Aufbau rule and the Hund's rule. That means in Aufbau rule states that, I am recalling here, who is not considering only about the 12 board examination, who is considering about the competitive exam also. That guys, listen it was carefully. So first one is Aufbau rule. Aufbau rule that states that the electron will fill up in the orbital according to their increasing energy. So that means the electron will occupy the position in the orbital according to their increasing energy level. Second one is Pauli's rule. About that here should I tell? But listen, Pauli's rule states that no two electrons can have same set of all the four quantum numbers. That means in an orbital there will be maximum 2 electrons and both will have opposite spin. Pauli's rule. And third one is Hund's rule. Hund's rule states that in a degenerate orbital means orbitals having same energy. Hund's rule states that in a degenerate orbital, the pairing of electron will not take place until all the orbitals will be singly occupied. Okay, so let's see here. That was, so for the first 3 electron, energy of T2g energy level is less. Energy of T2g is less. So first, second and third. So from first to third electron, first to third electron will occupy. First to third electron will occupy the space in T2g energy level, because from Eg energy level, the energy of T2g is less. So from 1 to 3, 1, 2, 3, first to 3 electron will occupy the position in T2g energy level. Now then after is fourth. So fourth electron, what happened here, when electron will occupy like this, Then after fourth electron will occupy here. If the energy required to pairing the electron will be less than that of EGL delta O. Difference of this one is delta O. Here delta O. This one is 2 by 5 delta O and this one is 3 by 5 delta O. Okay. So when the pairing energy, that means energy required to pair up the electron, will be less than that of delta O, then the fourth, fifth and sixth, this electron will occupy position in T2 energy level and pairing energy will be less when the strong field ligand will approach toward the d orbital. So the pairing energy will be less for a strong field ligand and it will be, the pairing energy will be less than delta O in case of strong field ligand and the pairing energy will be more in case of weak field ligand. So first to three, this one here, fourth electron will occupy the position in T2G energy level when the pairing energy will be lower than delta O. That means when the strong field ligand will have to do bond formation with the central atom, then the fourth electron will occupy position in T2G energy level. Okay. Okay, that is, and the fourth electron will occupy position in EG energy level when pairing energy will be greater than delta O. Okay guys, and keep in the mind, for strong field ligand, pairing energy will be lower than delta O, and for weak field ligand, the pairing energy will be greater than delta O. Okay guys, this one very easy. This one, okay. Here I am also explained. Here I shall also explain why the coordination compound shows color. So in case of this one here, very easy. For strong field ligand, the pairing energy is lower than delta O. So fourth, fifth and sixth electron will occupy position in T2 energy level. Then 7th, 8th and 9th, 10th, that will occupy position in Eg energy level. Okay, now let's see why the coordination compound shows color. Okay, so I shall discuss later on. Okay, that was here. Now bonding in tetrahedral coordination entity. Same here. Let's see. Since I have already explained about the bonding in octahedral complex by drawing, so you could understand this one very easily also in bonding in tetrahedral complex. Difference in the bonding in case of octahedral complex and the tetrahedral complex is that in case of octahedral complex, the energy of dxy, dyz and dxz was decreasing, and which was called T2g energy level, while the energy of dx square minus y square and the dz square were increasing, and that were called Eg energy level. The energy of T2g was decreasing through the value of 2 by 5 delta O, and the energy of dx square minus y square and dz square, that is Eg energy level, was increasing by 3 by 5 delta O. In the same way here, but in case of tetrahedral complex, the energy of dx square minus y square as well as of the dz square will decrease, and the energy of dxy, dyz and dxz will increase. So here the energy of dx square minus y square, firstly, once there will be bond formation, then the energy of these d orbitals will increase to this value, that will be called T energy level, that will be called delta T. The energy of the d orbitals will increase by the value of delta T. Then after, the energy of dxy, dyz and dxz, that will increase by the value of 2 by 5 delta T, and the energy of dx square minus y square and of dz square, that will decrease. So it will be called E energy level, and that will be called T2 energy level. Okay, there was T2g and Eg, but here only E energy level and T2 energy level. Watch out here, when you will add both of them, so that will be delta T only. So there will be energy will be conserved during the reaction, during the bond formation also. There be no creation or destruction of the energy. The energy will remain same only. Now for the 2 electron, so 2 electron will occupy the position in E energy level, because the energy of E level is less than that of T2 energy level. So first and second electron will occupy the space in E energy level. The third electron will enter in E energy level when pairing energy will be lower than delta T. So to pair up the electron, there will be less requirement of energy. So the electron will occupy the position in E energy level. And if to pair up the electron, there will be requirement of energy greater than delta T, then the electron will enter in T2 energy level. Okay, so first electron, second electron, if a strong field ligand will have to do the bond formation, then first electron, second electron, third electron, fourth electron. That means here when a strong field ligand will have to do bond formation, then first electron in E energy level, second electron in E energy level, third electron also in E energy level, and the fourth electron will also occupy the position in E energy level. While when weak field ligand will have to do bond formation, then what will happen? The first electron will occupy position in E energy level, the second electron also in E energy level. Then after, the third electron will occupy the position in T2 energy level. Third electron, fourth electron also, fifth electron also. Then sixth electron will enter in E energy level, seventh electron in E energy level, then eighth electron, ninth electron, 10th electron. Okay? Was it difficult? Same as that of the octahedral complex. Nothing else. Okay guys? Very simple here. Also we will discuss here the color compounds here. Next topic is, that's why I have left there. Let's see. This is important for you. Oh, here not written, so I am writing here. Why the coordination compound show color? So you have already seen that here d energy level, d orbital it is, energy of this d orbital has increased. Firstly, in case of octahedral complex, let's see. Then after, this degeneracy have not maintained, so energy of dx square minus y square and the dz square has increased, and the energy of that has been increased by 3 by 5 delta O, and the energy of this dxy, dyz and dxz that has been decreased by 2 by 5 delta O. Okay, so when light energy falls on the coordination compound, then the electron present in T2g energy level, in case of octahedral complex, that means the octahedral complex show color. Why? Because when light energy falls on the coordination compound having octahedral geometry, the electron present in T2g energy level will absorb some of the energy, and the remaining portion of energy will reflect back. When white light falls on the coordination compound, then the electron present in T2g energy level absorb some of the energy and jumps into EG energy level. The remaining portion of light reflects back, and that will fall in a particular color. That was about the octahedral complex. And in case of tetrahedral complex also, the electron present in E energy level, that will absorb some magnitude of energy, and the remaining portion of energy will reflect back. When white light falls on the tetrahedral complex, then the electron present in E energy level absorb some of the magnitude of energy and jump into T2 energy level, and the remaining portion of energy radiates, which will fall in the form of light, which will appear as of a particular color. Okay, so that is here. So in the 12th board examination, question frequently asked why coordination compound shows color. So you will have to write when white light falls on the coordination compound, then electron present in lower energy level, that is in T2g energy level in case of octahedral complex, and in E energy level in case of tetrahedral complex, and jumps into higher energy level, that is EG energy level in case of octahedral complex, and the T2 energy level in case of tetrahedral complex, and the remaining portion of energy will radiate in the form of electromagnetic waves, and hence the coordination compound will show the complementary color of which it has been absorbed. Okay, so that will be 12th mark question and frequently asked question that is. And this one is here. Usually I don't say you to mug up, but here if you will mug up, then there is some chances of asking the question from here. What is here? Like this compound here. Why that colors appear violet? Because that absorbs yellow color. If this compound here absorb blue green color, so that appears red. So that is both the color is of complementary. It has absorbed yellow, so appears violet. It has absorbed blue color, so has absorbed yellow orange. So red, so blue. Okay, so that was about the why the coordination compound shows color. That has been explained here. T2 energy level is energy level in case of octahedral complex of that has been shown. Now let's see here about that. You just read that, it's a theoretical portion. Only that much you read. This one you read, that has not a relevancy for the 12th board examination. But if you will read this one question 1-2 times, then you could answer this one for which will ask in NEET examination. Not so much important for IIT main examination, but in CUET there is some probability of asking that question. Now let's see about the limitation of crystal field theory. So let's see. So what's the limitation of crystal field theory? So here, in some cases, the ligands has been considered as point charges. Okay, and this one here, it account for the covalent. The crystal field theory has not taken into account the covalent character of bonding between the ligand and the central atom. You already know between the central atom and the ligand there is covalent characteristic, but the crystal field theory has not considered about that. Why there is covalent characteristic between central atom and the ligand. Okay, so these one have explained about the drawbacks of the crystal field theory has been explained in ligand field theory as well as the molecular orbital theory, which is about which you will have to discuss in higher classes. Okay, so crystal field theory has very effectively explained about why the coordination compound, show color, and how the shape of the molecules will determine, as well as the magnetic behavior of the compound also. But there is some limitation of the crystal field theory that it has considered the ligand as a point charge, and in some cases here the anionic ligands should exert the greater splitting effect. About that it has not given any information, and in addition to that it has not considered about the covalent characteristic between the central atom and the ligand. And third one here, so these drawbacks of the crystal field theory has been recovered in ligand field theory as well as the molecular orbital theory, about which you will have to discuss in higher classes. Now let's see in text questions. Explain this one. So better, I have already discussed about this one. You write by yourself. If anybody would like that he have written in such a manner that will get the full marks or not, then he or she may contact the YouTube channel of Educate. I shall read those answer and will inform that that particular guys will get the full marks by writing in that manner or not. And if not, then he should have to watch the video again, and if his problem will not get solved, then that may ask me personally also through the YouTube channel Educate. Then after is here. Why this one is paramagnetic and this one is diamagnetic? Very easy here. Then after is, so shape here will be, here pairing of electron will take place. So shape will be here a square planar, and shape here will be tetrahedral. Oh sorry, here both have the tetrahedral geometry, but it's diamagnetic and here paramagnetic, because here nickel is in zero oxidation state. About that you will have to study. Now this one is, why this one? Explain by yourself. Why inner orbital complex here? Because ammonia is a strong field ligand here. So here the inner d orbital will participate in the hybridization. There outer orbital will participate in the hybridization. About that you will have to explain. About this one, very easy you can do. Watch out. So no any question. No any text question here is that about which we have not discussed. So better will be that you answer this question by yourself. If feeling any difficulty, then watch out the videos, previous videos, and then after answer them. And even though if you will have any difficulty, then contact to the Educate. Now let's see bonding in metal carbonyls. About that we will discuss in next class. Okay, in the next class we will discuss about bonding in metal carbonyls, which is not so much lengthy. About that we will discuss in next video. Okay, it's all for this class. Thank you, Team Educate.